Hi everyone. In this example, I will explain you how to draw a root locus for a given system that we have here. The controller is given as Kp and the process is given as s+1 squared over s+2 squared. So it has two poles and uh, two zeros. We will draw the positive root locus and negative locus for this system. And then we will determine the values of Kp in R for which we have the closed loop system by Boyce table using both the magnitude condition of the root locus and the RAS criterion. So let's get started. So we have our L of S given as Kp over s+1 squared s+1 squared over s+2 squared indeed, okay? And we can rewrite it in this format. L of S is equal to rho times s+1 times s+1 over s+2 times s+2. So for this system, we have two poles, n is equal to 2. We have two zeros, m is equal to 2. As a result, r, which is the difference between n and m, is equal to 0. This means that there are no asymptotes for this system. Both branches will start from the poles and they will go towards the zeros and as rho goes towards infinity or minus infinity. So we can somehow start to draw the root locus for this system. This will be our positive locus, real axis, imaginary axis, and this will be our negative locus. And by negative locus, I mean values for rho between 0 and minus infinity. Positive locus rho is between 0 and plus infinity. We have two poles at s equal to minus 2. P1 is at minus S1 indeed is at minus 2 and S2 is at minus 2. These are the poles. And we have two zeros at minus 1. So I can start to draw them. Two zeros at minus 1. So I draw two circles to denote that we have two zeros. And two poles at minus 2. And same here. Two zeros at minus 1. Two poles at minus 2. We can determine which parts of the real axis belongs to the root locus in each case. So basically here we have 1, 2, and 3 regions. So parts of real axis. We have one section from minus infinity to minus 2. Next section is from minus 2 till minus 1. And the third section is from minus 1 till plus infinity. We can see that in all cases, we have even number of poles and zeros on the right hand side. So for example, if I pick a point here in this region, we have two poles and two zeros. In total, we have 4 poles and zeros on the right hand side of the test point, which is an even number. As a result, it belongs to the negative locus. If I take a point in this region, we have two zeros. And if I pick a point here, we have 0 number of zeros and poles. So in all cases, we have even number of poles and zeros on the right hand side of the test point. So here we have 4 poles and zeros on the right hand side of the test point. In this case, we have 2 zeros only on the right hand side of the test point, and here we have pose zero, number of pose and zeros on the right hand side. In all cases, the real axis belongs to negative locus. And I can show it here by highlighting the real axis. So none of the real axis belongs to the negative locus in it except the -2 and -1, because we will start from -2 and we will end up in -1. So as the next step, we can find out whether there are some break in or break away points as the next step. So we may have some break in or break away points. And to find out whether we have such a point or not, we need to find out the derivative of rho with respect to s and set it to 0. Then if we have any root, any real valued root, it would be either break-in or breakaway point. So we already know that 1 plus rho times n over d is equal to 0. As a result, rho is equal to minus d over n, and therefore d rho over ds could be obtained as minus d prime n minus n prime d over n squared. Okay, that's true, yeah, because we may have yeah, rho equal to minus d over n. So this is true, and we already know that n in this case is equal to s+1 squared, d is equal to s+2 squared. As a result, from here we have n prime equal to 2 times s plus 1 times s plus 1 squared, and from here, so is this correct? S plus, let's do it maybe not to make some silly mistake. I can write n as s squared plus 2s plus 1, so n prime would be 2s plus 2. D is equal to s squared plus 4s plus 4. As a result, d prime is equal to 2s plus 4, yeah. And now I can form what I get from here. So from here, I would say that we will have d prime n minus n prime d equal to 0. So d prime n is 2s plus 4 times n, s plus 1 squared, minus n prime d, 2s plus 2 times d, which is s plus 2 squared, equal to 0. We need to find out the roots of this equation, but looking here, I can rewrite it again here, like 2 times s plus 2 times s plus 1 squared minus 2 times s plus 1 times s plus 2 squared equal to 0. Looking here, I can say that s plus 1 and s plus 2 could be factored out. So I will have s plus 2 times s plus 1 times 2 times s plus 1 minus 2 times s plus 2 equal to 0. So here we can say that we have two roots, s1 equal to -2 and s2 equal to -1. And looking at the third part here, we have 2s plus 2 minus 2s minus 4 equal to 0. These s's will be cancelled out with each other. As a result, there's no root here. So in overall, we have two roots, s1 as -2 and s2 at -1. We need to determine whether they are a break in or break away. Break in or break away. I hope you know how to determine this. So the main way is to find out the second derivative of rho with respect to s, evaluate it at one of these points at -2 and at -1, and then depending on the sign, whether it's bigger than 0 or smaller than 0, you should be able to determine whether we have a local minima or local maxima, and as a result, whether it's a break-in or breakaway point. However, in the case of this example, by looking at what we have here in our graph, I can easily say that for the positive locus mainly, the branches will start to depart from the real axis as k starts from 0. So, and the point of departure will be -2, obviously, because it cannot be any other point. So s equal to -2 is a breakaway point, and s equal to -1 is where we have our zeros, and we know that the branches will go towards the zeros, and they are break into the real axis. So this is a break in point for us. And both of them belong to our positive locus, because so we can see that in the case of negative locus, the branches will remain on the real axis all the time. They will not depart the real axis. So what we need to determine in the next step is to find out the angle of departures and angle of arrivals. So let's see how to do this. We know that for the angle of departure, we have q times alpha departure equal to sum of phi i's minus sum of theta i's plus 2h plus 1 times pi for positive locus, and sum of phi i's minus sum of theta i's plus 2h pi for negative locus, in which phi I is the angle of the zeros with the pole indeed, and theta I is the angle of the remaining poles with the point for which we are calculating the departure angle. And let's see what do we have for this example. So since we want to calculate the angle of departure at this point, our test point is somewhere very close to the pole. The angles that we have from the zeros could be obtained in this way. So we connect the zeros to this point and then draw a line from the 0 towards plus infinity. Then find out this angle, which is equal to pi. So we have phi 1 equal to pi and phi 2 equal to pi as well, because we have two zeros. And we don't have any other pole except the ones that for which we are finding the angle of departure. So as a result, we will have 2 times angle of departure equal to pi plus pi minus 0 plus 2h plus 1 times pi for positive locus, and pi plus pi minus 0 plus 2h times pi for negative locus. Since we have two poles here, we will set h equal to 0 and 1. Therefore, we will have 2 alpha departure equal to 2 pi plus pi and 2 pi plus 3 pi for positive locus, and 2 pi and 4 pi for the negative locus. Or in other words, alpha departure will be equal to 3 pi over 2 and 5 pi over 2, or we can say pi over 2 for positive locus, pi and 2 pi for the negative locus. You could also have get rid of two pi's at the beginning, but that's fine. So we can see here that for the positive locus, we will have branches departing from the poles at -2 with the angle of 3 pi over 2, which is this one, and 5 pi over 2, which will be equal to pi over 2, or this one. This will be for the positive locus. In the case of negative locus, the branches will depart from the poles with the angle of pi and 2 pi, or 0. So then the next thing that we need to find out is this is for negative locus, this is for positive locus, is to find out the angle of arrival at zeros, for which we have q times beta arrival equal to minus sum of phi i's plus sum of theta i's plus 2h plus 1 times pi for positive locus, and the same terms plus 2h pi for negative locus. And here we can find out theta i's. So we have the poles here and 0 over there. In order to find the angle from the poles to the 0, we just need to connect the pole to the 0, draw a line from the pole towards the infinity, and then find out the angle between these two, which in this case is obviously equal to 0. So we will have theta 1 equal to 0, theta 2 equal to 0, and since there is no other 0 in the system except the one for which we want to find out the angle of arrival, there will be no phi I. So as a result, we will have q times beta arrival equal to 0 plus 2h plus 1 times pi for positive locus and 0 plus 2h pi for negative locus. Q is equal to 2, so 2 times beta arrival will be equal to, setting h equal to 0 and 1, because we have two zeros here, we will have pi and 3 pi for positive locus, and 0 and 2 pi for the negative locus, and dividing by 2, beta arrival will be obtained as pi over 2 and 3 pi over 2 for positive locus, and 0 and pi for the negative locus. So this is how we can determine the angle of arrival at the zeros. We see that for positive locus, we will have the angles equal to pi over 2 and 3 pi over 2. It means that we will have two branches coming to the zeros with these angles. And for the negative locus, so this is for positive locus, for negative locus, the branches will arrive at the zeros with the angle of 0 and pi. So one will arrive from this side and the other one will arrive from the other side. So having all this in hand, now we can go back to the original graphs and plot the root locus. So starting from the positive locus, we know that we will have two branches departing from the poles here with the angle of pi over 2 and 3 pi over 2, and they will arrive at the zeros with the angle of pi over 2 and 3 pi over 2, and they will never cross the real axis. So this will be somehow the root locus for the positive values of rho, as I draw it here, and these branches will be symmetric with respect to the real axis. Yeah? So this is what we will have for the positive locus. In the case of negative locus, The branches will start from the pose. They will depart with the angle of pi and 0. They will arrive at the zeros with the angle of, again, pi and 0. So one of them, as we can see here, will go directly towards the 0. And the other branch will go towards infinity, minus infinity. And after a while, it will come back towards the 0 from the other hand. So this will be what we can have as the root locus for the negative values of rho. Yeah, this is for negative locus, and this is for positive locus. So this is all that we have as the graph or the root locus. Now let's see what was the question here. I will also draw it with MATLAB and show you. You can compare it with this. We need to find the ranges of Kp in R such that the closed loop system is BIBO stable. And for that, we will use both the RAS criteria and the magnitude condition. So first of all, looking here, we can see that for positive values of rho, or Kp here, because rho is equal to Kp, for positive values of rho, our system is always stable because we have no pose on the right-hand side. However, for negative values of rho, our system sometimes becomes unstable, and for some values, it stays stable. So we need to find out what is the value for which our system changes the stability somehow. Yeah. So this is the way in which the value of rho changes, goes towards minus infinity. So here we will have some value. After that value, going towards minus infinity, our system will remain stable. And at the same time, we see that here, starting from 0, we are stable. Then going towards some value, our system becomes unstable at some point. We will find out what's the corresponding value of rho here and also here at the when one of the poles indeed becomes or is located at the infinity. So let's see how we can do it. As the first approach, we will use the let's use the RAS criteria, yeah, as the first step. We have 1 plus rho times n over d equal to 0, or in other words, we have d plus rho times n equal to 0. D is given as s squared plus 4s plus 4, and rho times n, which is s squared plus 2s plus 1, equal to 0. And from here, we will have s squared times 1 plus rho plus s times 4 plus 2 rho plus 4 plus rho equal to 0. Now we can form the RAS table S2, S1, S0, for which we will have 1 plus rho, 4 plus rho, 4 plus 2 rho, 0, and 4 plus rho. I hope you know how to form the RAS table. And now, if you want to have our system stable, what we need here is to have the first column, all the elements in the first column having the same sign in it. If we have 1 plus rho bigger than 0, 4 plus 2 rho bigger than 0, and 4 plus rho bigger than 0, our system will be stable. At the same time, all of them could be smaller than 0. Or we can say 1 plus rho is smaller than 0, 4 plus 2 rho is smaller than 0, and 4 plus rho is smaller than 0. Still, our system will be stable. And let's combine all these together. So from here, I could say that rho should be bigger than -1. Rho should be bigger than minus 4 over 2 or minus 2, and from here rho should be bigger than minus 4. Combining all of these together, we will get rho bigger than minus 1. So if rho is bigger than minus 1, the system is stable. And from the other side, we have rho is smaller than minus 1, rho is smaller than minus 2, and rho is smaller than minus 4. Combining them with each other, we would say that if rho is smaller than minus 4, our system is stable. So this is, both of them are true. So we will have rho between minus 1 and infinity, and rho between minus 4 and minus infinity. This is the range for which our system is BIBO stable. The closed loop system is BIBO stable. Now let's see how can we find out these values, rho equal to minus 4 and rho equal to minus 1, which are the marginal values for the rho indeed. But however, this time we will refer to the root locus graph that we have here, that we already have drawn, yeah. And we will deal mainly with the negative locus because it's indeed the important part here. So let me maybe just draw it again here. For the negative locus, where rho is between 0 and minus infinity, we have this situation, two zeros here, two poles here. One of the poles goes towards 0 in this way, and the other pole goes towards minus infinity, but at some point it comes back to the positive values. It moves towards the 0 like this. So one important point here is when the branch crosses the origin that we have here. So what's the value of rho here? We can just write determine the value of rho by using the amplitude condition for the root locus. So we know 1 plus rho times n over d is equal to 0. Or in other words, n over d is equal to minus 1 over rho. And from here, we know that amplitude of n over d evaluated at s star should be equal to amplitude of 1 over rho. Here s is equal to 0 or s star is equal to 0. As a result, amplitude of n over d at s equal to 0 can be obtained as, so n is s plus 1 squared. Let me just write it again here. S plus 1 squared, and d is s plus 2 squared. As a result, amplitude of n will be equal to 1. So here we have minus 1 and minus 2. And the amplitude coming from the d will be equal to 2 to the power of 2, which is 4. And this is equal to minus 1 over rho. Therefore, amplitude of rho is equal to 4. And since we are in the negative locus, the value of the sign for the rho will be minus, or rho will be negative. As a result, rho is equal to minus 4. So this is the first point that we can make. And from here, we say that if rho is smaller than minus 4, we have a stable system. Now we need to find out the other marginal value for rho, which is minus 1 here. And let's see how to determine it indeed. So it's a little bit tricky for that, because for that value, we will have one of the poles at infinity, somewhere here. And for that, we can write down the amplitude condition again. So we need to find n over d at s equal to infinity, or s going towards infinity. And it should be equal to amplitude of 1 over rho. N over d we already have. So amplitude of s plus 1 squared over s plus 2 squared as s goes towards infinity, and I think you would agree that this value is equal to 1, because we will have s squared in the denominator, s squared in the numerator as s goes towards infinity, and the result is equal to 1. So amplitude of rho is equal to 1, and since again we are dealing with the negative locus, the sign of rho will be negative, so rho will be equal to minus 1. And from here we can say that if the value of rho becomes smaller than minus 1, so rho is smaller than minus 1, and at the same time if it's bigger than minus 4, the system will become unstable. And that's what we already have obtained here. Yeah. So rho, the system is stable only for these values, rho bigger than minus 1 and rho is smaller than minus 4. Okay, so that's all in terms of the calculations. The only part that is missing is to show you how the root locus looks like when we do it with MATLAB. I will do it now and then show you the results. So here you can see how I plot the root locus for the given system. G is defined by TF command. And then I have a figure in which I'm plotting the root locus for the positive locus and for negative locus as well. MATLAB by default plots it only for the positive locus. To have it for the negative locus, I just have added the minus sign in front of the G. And here I can show you what I have obtained. So the first one here in the upper part is the positive locus, and the one in the lower part is the negative locus, and you can already compare it with what we have obtained here. Yeah. So we have two branches in terms for the positive locus departing from the poles here going towards zeros, and the same thing for the negative locus, in which one branch started from the pole and it has gone towards the 0, and the other branch started from the pole, has gone towards minus infinity, and then it has come back to the positive values, and it has ended up in the other 0 indeed. So you can see that what we have obtained coincides with what MATLAB provides us. Okay, so this is all for this example. I hope you have enjoyed it and you have learned something in different aspects. If you have liked it and you think that it would be useful for some other people, don't hesitate to share it. And that's all for this video. Thank you for watching and see you next time.